Okay, thank you for the invitation. Okay, it's a great pleasure to give a talk here. And so I'm a full professor at the University of Latvia. Okay, so I finished my PhD in 2014, so some time ago. Okay, and I'm mostly working on quantum algorithms and quantum lower bounds, and so query complexity, quantum walks, things like this. Okay, and so today, okay, my presentation will be about lower bounds, which I find quite rather intriguing and interesting. Quantum query lower bounds. Okay, so let me start with the talk. Okay, so it's a tight quantum lower bound for k-distinctness. Okay, and first, so I have quite a number of slides here, and I've been told that I have almost 1.5 hours. So it's possible I will cover all of them, which actually was not expecting to do. Usually I can't do that. Okay, but okay, so first I would like to introduce the problem. Yeah, so on one thing, if you have questions, yeah, please interrupt me at any time and ask them. Okay, and yes. So the problem is k-distinctness. So we're given a string x, okay, of n elements from some input alphabet. Okay, and the task is to find k elements that are equal, or alternatively, the decision version is to tell whether there exist k equal elements. Okay, and so search and decision versions are essentially equivalent. Okay, so in this talk, I will consider the search version. Okay, so we will have to find k equal elements, okay, their positions. Okay, and the case k equal 2 is known as element distinctness. So element distinctness is exactly the same thing as 2 distinctness, so just a different name. Yeah, so why I'm interested in this problem? Okay, I think not only me, but other people as well, that this problem inspired really a number of techniques in proving both upper and lower bounds on quantum complexity. Okay, so let me let me support this statement by brief history overview. So the first algorithm to this paper is from 2000 by Burman and a bunch of other people. Okay, so this gives order of n to 3/4 query time algorithm for element distinctness. So element distinctness is the special case of k equal 2. Okay, and so this was used using quantum amplitude amplification. So actually nothing too fancy here. Okay, but the next thing was interesting is the lower bound, also for element distinctness. It is due to Aronson and Shi. So actually this lower bound is more known as lower bound for the collision problem, which is cube root of n for the collision problem. Okay, and this immediately by simple reductions gives an omega n to 2/3 lower bound for element distinctness. Okay, and it was obtained using the polynomial method. Okay, so I will come back to polynomial method actually back in this talk later. Okay, and a year later, Ambinis I came up with an upper bound, both time and query. So it's time efficient up to log factors, assuming you have a powerful form of quantum random access memory. So something I will not talk today. And so what was used, so this was really a brand new algorithm applied to this problem. It was a quantum Wilkins-Johnson's graph. Okay, and so this gives a tight algorithm and to search for element distinctness, which is, as I said, the special case of when k is equal to 2. Okay, so then a decade later, I myself came with an improved upper bound. So it was just a query complexity, not a time-efficient algorithm. And that is something which is n to 3/4 minus something which is exponentially small in k. So like the exact expression is on the slide, you can see it. So essentially as k grows, it approaches 3/4 very fast. But it's like improvement to the Ambinis algorithm because as k grows, it approaches 1. It approaches linear algorithm. Here it's n to 3/4. So for any constant k, no matter how large it is. Okay, it was used also using modification of learning graphs, which is a special case of electric quantum walks. Okay, and that was not the first application, but the second application, and it was also a modification thereof. Okay, and so the next year there was a time-efficient algorithm which gives exactly the same complexity. Like if you plug in that expression k equal to 3, you get to 5/7. Okay, and so it's two different papers which were later published as a merged paper due to myself, and another paper was due to Child, Jeffrey Kothari, and Magnia. And so it used two new techniques. It used electric quantum walks, and it used nested quantum walks. So all just to solve this problem. Okay, now let's go to the lower bound side. So there was actually two papers which I just cite as one paper because they used very similar techniques. It was Ban, Kothari, and Maurer, also Mande, Tower, and Zhu. Okay, so it's also n to 3/4, but minus something which is linear in k. So exactly as k grows to infinity, it also approaches 3/4, but slower than the upper bound, and it doesn't really give you anything interesting for k equals 3. So for k equals 3 and k equals 4, it's just the same complexity we had before. Okay, and it was used dual polynomials, which is a different way of a different flavor of the polynomial method. And quite recently, no, it's like 4 years ago, but feels really recently, Jeffrey and Zur came up with a time-efficient algorithm, which has exactly the same complexity as the query efficient algorithm do it myself. Okay, and it was also application of a brand new technique they coined multidimensional quantum walks. And yeah, so this is just an overview. So the three important points, which just outlines the complexity. So this is the query upper bound, the best known query upper bound, the best known query lower bound, and the best known time efficient algorithm. Okay, and so in this work, which is a paper, and so is a tight lower bound which matches for any constant k, matches the upper bound, okay, with a small caveat that the size of your input alphabet should be, which is denoted by q, should be quadratic in n, quadratic in the number of elements. Okay, and so this again is achieved using a new lower bound framework. Okay, and so in this talk, okay, so I will mostly talk about the framework. And so when we cover the framework, and I still have some time, I will talk about the k-distinctness problem. Okay, but the emphasis will be on the framework, because if I don't explain the framework, it's somewhat hard to explain the lower bound. I think so. Okay, and so let me just explain this framework in a bit more detail. So this Iron, Shanxi, Ban, Kothari, Tower, Mande, Zhu, so all the papers which are on the lower bound front of this problem, they all use the polynomial method, either directly in the form of Patoury's lemma, or like indirectly, like the dual polynomials. Okay, and another important lower bound method, which was not applied to this problem, at least in the form I stated it, it's the compressed oracle technique, which is a famous technique due to Zhandry from 2017. Okay, so this technique is rather intuitive. Okay, so but it has a restriction that it's restricted to the original form, restricted to uniform probability on the input string. So you can prove lower bounds on the average complexity, assuming that your input comes from a uniformly random input string. Yeah, it's there was some follow-up work which somewhat relaxed this condition. Actually, there was the last QIP, there was a paper on permutations, which was really important for the quantum cryptography field. Okay, and for most problems like k-distinctness, like if you're interested in the worst case complexity, then the uniform probability is not the correct thing you should look at. Okay, and so actually, Will and Zhandry in the same year, 2017, they characterized complexity of finding k-collision using under this assumption that we have a uniform random string. So this should not be confused with what I did in this paper, although the techniques look similar and the bound also is somewhat similar. Okay, but there is like a difference between if you're assuming there is a uniform random string or just a worst case. So the worst case complexity is harder. For instance, the algorithm for the uniform random string is much simpler than the algorithm for the worst case complexity, and it's like really much harder. Okay, and so in this paper, I'm using a different technique. I can show, I will show you, is actually a generalization of the polynomial method. But if you take it, how it looks like, it's more inspired by Zhandry's ideas, and I think that Zhandry method can be somehow filled into this framework. I haven't really worked out the details, but I think there should be some connection because it looks very similar. And so the main difference with the Zhandry is that it works for non-uniform distributions. Okay, so any questions so far? Okay, so let me go to the Belovs. So this is the next section, and so this is essentially what I think is the most important, both for the polynomial method and for the Zhandry method. But okay, but it looks more like you can also think about this section as a somewhat overview of Zhandry's ideas. Okay, so the problem. So this framework can be used for other problems, not just essentially k-distinctness. Okay, so you assume that the algorithm has oracle access to the input string in some alphabet of size q. Okay, so it's very general. And those are, I'm assuming, relational problems. So k-distinctness, as I said, was a search problem. So there can be different positions where there are k equal elements that you're searching for. So this is a case of a relational problem. So where each input can have several correct outputs. Okay, and they are all out of some set of responses, which I will denote by capital R. Okay, and okay, so so there will be a piece of notation that I will remind what it means when we come up to it. So MR will be the pre-image of MRO will be the pre-image of RO. Okay, so this is the set of inputs for each RO is the correct output. So I'm just taking all the inputs, and for each input there can be several correct outputs. So I'm taking all the inputs for each RO is correct and not otherwise else. And so MRO can intersect between different sources. So let me now explain, so remind you of quantum query algorithms and quantum query complexity, how it looks like. So this is a common picture above of a quantum query algorithm. So it has 3 registers, of which 2 are important to us. It's I, and C. Okay, and W is just some working register of the algorithm. Okay, and so the algorithm alternates the unitaries. So in this case, we are only interested in query complexity, so we are not counting how complicated it is to implement different unitaries. Okay, and the applications of the input oracle. That's the only thing how the algorithm can get information about the input by applying these input oracles. Okay, and so I will assume that the queries to this input oracle, OX, are in the phase. So this means that, okay, it acts like this. So it takes 2 registers, I and C. Okay, where I is, so both of them are, so I is contains one of the n elements. So it goes to the xi, to the ith elements of the input strings, and C contains one of elements of zq. Okay, and so it multiplies the phase by omega q to the power of c xi. So this is an oracle. This is a standard oracle in the phase, and it's equivalent to the oracle in the register. So we will see in a moment why we're using in the phase, the oracle in the phase. Okay, and so yes, and omega q is the primitive root of unity, if I didn't tell it. So it's e to the power of 2pi divided by q. So omega to the q is 1. Okay, and so I also introduce some notations. So psi xt is the state of the algorithm on the input x after t queries. Okay, and have primed and non-primed versions. This actually means whether it is before or after the application of the unitary. Okay, so you can see the states above in the diagram. Okay, so the complexity of the algorithm is the number of queries. So this is just t. Okay, and at the end, some orthogonal measurement is performed. So without loss of generality, I can assume that it's not this orthogonal measurement. Okay, so it's P rho, where rho ranges over the set of responses. So again, I can assume that the measurement is given by the outcomes. Okay, and so the probability the algorithm outputs rho and input x is given by this probability, so norm squared of the corresponding projection. Okay, so now I'm doing a thing that is pretty standard and had been used before. So I will introduce another register, which will not be available to the algorithm, but it will store the input string. So I will call it the input register. So I will denote it by script x, so just x. So it's a product of x1 up to xn. Okay, it stores the input string. So xi is equal to c to the q. So it's a qdit. Okay, and so the input string is just stored as usually as a product of the corresponding elements of the standard basis. So it's x1, x2, all the way to xn. Okay, so when we introduce this input register, so the next thing which was used before, just we add it to the algorithm. So to the space of the algorithm more correctly. Okay, so that the so the unitaries are still working in the so the UI applied to the space of the algorithm. Okay, but the input oracles somehow interlines this input register with the space of the algorithm. So it's not directly assessed by the algorithm. Okay, but it's assessed via this input oracle. So now it's just O, because it doesn't depend on the input register. This input register is just another sorry, input string is just stored in the input register.
Sorry, I have a small question. So
yes,
this
sure.
W register is what do we know at this moment? That do we restrict W in some way?
No, W can be anything. So if we are talking about this space, it's just working space of the algorithm. So it's where the algorithms actually, for the algorithm, it's the most important part. Is actually where it stores everything. Okay, from our case, we're just working at the queries. It's like not important at all. Yeah, but it can be anything of any size. Yes.
So probably we can track while you present your work, right? When I see that what you are storing in W.
Sorry, I didn't get that.
So I think you will not worry, but let me see if I can track what you are storing in W.
Yeah, so W will not be of much importance here. Yes, so as you can see, like the input oracle, which is the important thing, doesn't use W.
Okay, thank you.
Yeah, any other questions?
A quick question. So,
yes.
So here we are assuming that the X register starts in the uniform superposition.
Yes. Yes.
So
yes.
Going ahead, do we want to also look at distributions which are non-uniform?
Yes, exactly. So
okay,
I will talk about this. So you can see there's a section non-uniform distribution on the left-hand side. So I will get there. Yeah. So yeah. So thanks. So that's exactly what I've been going to. Is that I will assume. Okay, actually, it's how Zhandry works. So this is like pretty much everything due to Zhandry. Everything in this section. But quite interestingly, I will note it here that if you take the original unbiased paper on the adversary lower bound, I think it was called quantum lower bounds by quantum arguments, something like this, this has exactly the same picture. So it's quite curious. And so it's like, seems to be like some similar ideas. So this paper is already in the original paper due to unbiased. Okay, but not this assumption that we have this uniform state of the algorithm. So I'll introduce uniform states of the algorithm, which are just psi t and psi t prime, so without x this time. So this is just a uniform superposition of the states we had previously. So maybe let me go back to slides. So here we had psi xt, which depend on the x, and so this somehow combines all of them in one state, which we call the uniform state, because it's the uniform superposition over all the inputs. Okay, and so why uniform is cool? because it is part of the family of the Fourier basis. Yeah, so exactly again, I will introduce the Fourier basis. So you should be familiar to this, but just in case. So in C to the Q, where again Q is the size of the input alphabet. Okay, Fourier basis is given by these hatted strings. Okay, so a hat, which is just this expression. Okay, you must have seen that. Okay, and in the input register, which is a product of n copies of this register, so the Fourier basis is just given by tensor products of the Fourier basis in the corresponding registers. Okay, and so I can think about it as the labeled by a string, which I will denote by sigma, small sigma. And this small sigma lives in the space zq to the n. So the input string x and the Fourier basis string sigma, they live in the same space essentially. They live in zq to the n. Okay, and yeah, and so I can write the initial uniform state of the algorithm as in a more concise way. So this funny notation, which is empty set hat, stands for the identical zero function. Yeah, so function which is zero on all elements. Okay, and so why it is like this, so I will explain in a moment, but essentially I will assume, which if it is not stated otherwise, I will assume that the value of the function sigma is zero. Okay, and so I will just denote the positions where sigma is non-zero. So there are no such positions, so it's an empty set. So this means this function is a uniform zero function. Okay, so it's just one part of the Fourier basis. So one element of the Fourier basis. Okay, and so this allows to give this important idea, which is I think the first time I see so in Zhandry's paper. This is this phase kickback idea. Okay, yes, of course, phase kickback is more older than this. Is older than this, but okay, this particular formulation is I saw in Zhandry's paper. Okay, and so this is how the input oracle works. If you write the input string in the Fourier basis, then it has a very nice form. So this adds, so this adds this function here. So I don't have it written down. Sorry. So what's meant here? So this sigma is a function, as I had on a previous slide. Okay, and this ai maps to c is a function such that sigma of I is equal to c, and sigma of I is zero everywhere else. So I had a slide. I got lost it during preparations. Sorry. Okay, so essentially the input oracle just adds the value of c to sigma I. Okay, and so this is a very simple thing, but I think I will give a proof. So it's like a one-line proof that will take me 3 slides. Okay, and just because if you just want to really remember anything from this talk, I think this is like the most important thing. So it's a very short and neat argument. Okay, so this is the statement what I had previously. So this is how the input oracle works. And so here I'm using that the input oracle works in the phase. So it multiplies by this phase omega q to the power of c xi. Okay, and so this is a statement of what the Fourier basis is in CQ. So let me just write this state here in a more explicit way. So it's just a multiplication of sigma 1, sigma I, sigma n, so the product of these guys. So sigma I will be important here because this register contains I here. Okay, so let me write it out, how it looks like. So that's exactly the same expression as here, with A replaced by sigma I and B replaced by xi. So otherwise, it's exactly the same expression. Okay, so now I am applying the input oracle, which multiplies by this phase here. So after the implication, I get this additional cxi phase. Okay, which I can just just add to sigma I. Okay, and so this is again an element of the Fourier basis. Okay, this is sigma I plus C. Okay, and so that's that is this state here on the right hand side. So the effect of the input oracle is just sigma I gets updated with sigma I plus C. Okay, and so this is like really nice, because then we can see that the oracle actually acts in the space X, not in A. Now how we could see that the input oracle acts in A, but like from this point of view it acts in X, and we have much more control about X because we know everything about X, and we know pretty much nothing about A because of this W that we've been asked previously. And this also gives an important piece of intuition, which will be really important in my presentation, that the state sigma hat has knowledge in some way about the variables in the support of sigma. Okay, the support is the set of the set of indices where sigma I is non-zero. So this is the support. And equally, and more importantly, it has no knowledge whatsoever about the variables outside of it. Okay, in particular, we had the following corollary, that after T queries, the uniform state of the algorithm, it doesn't matter whether it's psi T or psi T prime, it lives in this subspace, X at most T, tensor product A, okay, where A is just the space of the algorithm, but X at most T is spanned by all the Fourier elements of the Fourier basis, sigma hat, which has support size at most T. Okay, and so intuitively, it says that the algorithm, okay, so algorithm is in superposition, as usual, it's a quantum algorithm, but if you take each branch of the superposition, has knowledge only about the value of at most T variables. Okay, we don't know where these T variables are located, but we know that each branch of the superposition knows at most T variables, which is quite natural because it has made only T queries. Okay, so this is a way how to formalize this intuition. Okay, and so we'll be working on like making it more precise. In particular, stating like what variables the algorithm knows precisely. Yeah, so any questions about this so far? About the pillars? Okay, now, so all of this was for uniform distribution, as was already mentioned. Okay, now let's go to the non-uniform distribution. And how we go to it, it's like very simple. Okay, so as I said, we use uniform probability distribution as input. So assume we want another probability distribution. So assume we want worst case probability distribution for some, so Yau's kind of probability distribution for some problem. P, which is like non-uniform, something different. Okay, so to keep track between uniform and non-uniform things, I will introduce another register Y, which so far will be isomorphic to X, but just now, for now, just will indicate that I'm talking about non-uniform distributions. And I define a very simple transfer operation, which goes from X to Y, so from uniform to non-uniform. It's a linear operation, and it's just a diagonal operation which just substitutes the probability in the uniform distribution 1 over the square root of q to the power of n with the square root of px, which is px is the probability in the probability distribution I'm interested in. Okay, and square roots because this is quantum. So amplitudes are square roots of the probabilities. Okay, and so it's obvious if you take psi t, which is the uniform state of the algorithm, and you apply this upsilon. So this letter is upsilon, if you're wondering. So upsilon psi t is just goes to again the combination of the states of the algorithm psi xt, but with the probabilities given by the square root of px. Okay, so the transfer operator, this upsilon, it's linear operator, but it is not unitary. Okay, but we don't care. Yes, looks like too simple to work, but turns out it works. So let me give you one piece of technical slide. One piece of technicality is that this anti-concentration notion, which is also in some way is in Zhandry's paper. Okay, and so it will be used in the lower bound framework quite importantly. So I will be using this gamma parameter, which is a real number between 0 and 1. Okay, and I will say that a vector phi, which lives in this like non-uniform space y, which is just like a linear combination of the inputs, is gamma anti-concentrated if the norm of m rho phi is at most gamma times the norm of phi. Where you call this m rho, that was the projection over all the inputs for which rho input strings for which rho is the correct output. So I'm taking my long vector phi, and I'm taking the subvector of it which corresponds to the inputs for which rho is the correct output, and I'm claiming that it's gamma anti-concentrated if I'm taking this subvector for any rho in the which is a response of the algorithm. For any rho, it is the norm drops by a factor of gamma. Okay, so it's somehow it's not biased towards any particular output. That's what's stated here. So if gamma is small, it's not biased toward any output. So any output somehow is not likely. Okay, then like two more technicalities. A subspace of y, so h of y, is gamma anti-concentrated if all vectors in this subspace are. So just to warn you, like this anti-concentration is not closed under addition. So the set of anti-concentrated vectors is not a linear subspace. Okay, but in this case, I'm just considering that this subspace just happens to consist of all anti-concentrated vectors. Okay, and this another like thing is vector psi in gamma times a, where a is again the space of the algorithm, but can be particularly any other space, is strongly gamma anti-concentrated if psi belongs to some h times a. So I can take a subspace h of y, and so psi still lives in this subspace, and h is anti-concentrated, so it consists of anti-concentrated vectors. Okay, so I don't need this. So this is a technical thing I need. But what we really have to think about that this anti-concentration means that it is non-biased towards any particular output. So it's somehow smeared over all possible outputs. So if you're trying to guess any output, if you're in this state, you are unlikely to succeed. Okay, and so this proposition makes it formal. So if the final state of the algorithm, which is upsilon psi t prime, so again, so psi t prime was the final uniform state of the algorithm, and where I'm applying upsilon, I'm going to this new probability distribution. Okay, so the final state, if the final state is strongly gamma anti-concentrated, so this is the last thing here, then the average success probability of the algorithm, so with respect to this probability distribution P, which I care about, is at most gamma squared. Okay, so if it is smeared over all possible outputs, then the algorithm cannot like guess the correct output, so it cannot output anything reasonable. Actually, it's quite easy to prove this proposition, but okay, I will not go into that. Okay, okay, and interestingly, this gives a way of stating a polynomial method, mostly in the form of the dual polynomial. Okay, and so the polynomial method proves lower bounds in quantum gradient complexity of a partial Boolean function, okay, a total Boolean function, f, by showing that f cannot be approximated by a low degree polynomial. So again, I will not go into detail, but it turns out, so it's in the paper, so this is a special case of the construction from the previous slide. The subspace upsilon x at most t. So if you recall this x at most t, okay, maybe I can go back to my pillars, and we have this phase kickback thing. Okay, so if you remember this corollary, that after t queries, the algorithm lives in this space x at most t. Okay, so let me go back where I was polynomial method. Okay, so this okay, so if I'm applying epsilon to this, so epsilon again goes to this probability distribution that I care about. So it is 1 over square root of 2 anti-concentrated for a carefully constructed p coming from a dual polynomial. Okay, so the dual polynomial is a way how you show that your function cannot be approximated by a polynomial. So from this dual polynomial, you can come up with a probability distribution p. Okay, and with this probability distribution p, it turns out that this subspace, this whole subspace, is 1 over square root of 2 anti-concentrated, and this is the best possible you can get if you have only 2 outputs. Like it just means that the algorithm outputs correct answers probability 1/2. Just it's the same as just guessing. And so the problem with the polynomial method, also it's like a very powerful technique and been used successfully before, as I explained in my history slide. Okay, such p's are very unnatural and contrived. Okay, and so what we would like is to use something similar, but for natural probability distribution p. Okay, so any questions maybe at this point before I move on? Okay, go good. So now I will need a bit more of technicality. So I will introduce a type of input. Okay, and so a type means just some collection of inputs which are, from my point of view, kind of similar. Okay, and then for each input in y, okay, so y is just the input with this probability distribution p, which is non-uniform. Okay, so I will just represent it as a pair mu y. Okay, so where mu is a type, so it can be, in principle, it can be anything, but I can practice it because I will just show an example shortly. And so y is the same input string as before, so just additional piece, like which is handling just for each input, I have additional type attached. In fact, I can have different types attached to the same input as well. And I will like to do that lately. Okay, and so inputs with the same time are simple. In particular, what I'm assuming is that they have the same set of correct outputs. So that's important for me. So the output doesn't really depend on the input y, it depends on the type. Okay, so for the k-distinctness problem, okay, types are given by partitions of n, right? And so where the partition is just the usual thing, I and j are in the same block of mu if yi is equal to yj. So this kind of partitioning is the same as a hidden subgroup problem, where this partition into cosets. Okay, and the function has the same value on each coset, but the different values between different cosets. And so for k-distinctness, you can also think in the same way. So the inputs is given by partition. So what we're interested is which elements are equal and which elements are distinct. You don't really care about the particular values. So that's why you're getting these partitions. Okay, and so the output is also depends only on this partition. So the output is correct. So the output is a k-tuple. So it should consist of equal elements. Okay, if it's contained in one of the blocks of the partition, so this is a correct output. Okay, so again, so this is like a piece of notation which I needed. So y at this point is spanned by mu y. So I'm adding this type to the input. And now I have this y mu, which is spanned by mu y, where mu is fixed. Okay, so particular, just the whole set y is just the direct sum over y mu over different mu. So this is decomposition into orthogonal subspaces if you fix for fixed mu. Okay, then I have like probability distributions. Like, so p mu y is the same thing as p y before. So this is just probability of particular input. Okay, so p mu is the probability of particular type. So that's the sum over all y's of all inputs that has type mu. Okay, so this p prime is just conditioned probability. So p mu y divided by p mu. Okay, and so I can define, so previous has this transfer operator which goes from x to y directly. Now I'm going from this restriction of it. So it's epsilon mu. So we'll see why I'm using this in a moment. So this epsilon mu, it's only moves to the input with type mu. Here it goes from x to y mu. So that the actually the epsilon of psi is just the direct sum of epsilon mu phi times the square root of pm. Okay, so you can see that this psi phi is again divided into blocks, where each block depends to a different partition. Okay, in this case, these blocks do not intersect. So, say I'm thinking about this epsilon phi as a block vector, where each block corresponds to one particular type. Okay, so now why I'm using all this is this knowledge operator and the knowledge system. Okay, so for each mu in M, okay, which is a type, I define the knowledge system that consists of all subsets of N that have crucial knowledge about every input with type mu. Okay, again, this is a vague statement. In principle, you can take any system, any set of subsets of N, but okay, in practice, it makes sense to take something reasonable. Okay, and k-distinctness. So again, this is what we had before. So types are given by partitions, and two input indices E and Y are in the same block if they have the same value.
Sorry, can I ask something?
Yeah, sure, of course.
So I think everything depends very closely on this type mu. So can you say a little bit more that how are you deciding this type here in your problem?
Okay, for arbitrary problem, it can be like this is a mathematical formalism, and you can take it whatever you want. So, for instance, you can take type to be equal to input string, and so this means you're not using types at all. Like each input string has its unique type. But for me, it's somehow helps to break the set of inputs into different blocks and treat one block as a single entity. That's why I'm introducing these types.
Yeah, and
Okay,
like
yes.
you have a property for the block, right? So this is related to the distinctness problem. So can you say a little bit more?
Yes, I was just about trying to state this. Yes, okay, so let me go back here. Okay, so this is like was just the next point on the slide.
Okay.
Okay, so yeah, so this so the type was as before. So as I said, the type is just a partition, like where in each block we have the same elements with the same value. Okay, and so now this element S belongs to the knowledge system. Informally, so I should have said that. Informally, this means okay that it has some kind of certificate. Because I'm thinking about it as having a certificate, but maybe it's something different. Can be something different. Need not be a certificate, but in this case, it is a certificate. So in this case, is S has intersection of size at least k with some block of mu. Okay, which means recall that the blocks, each block of mu contains equal elements. So this means that S contains k equal elements for each input of type mu. So just if you know this S, and so it has this subset of k elements which comes from the same block, so it can output this intersection says these k elements are equal. Okay, so if it knows the values of the element in S, it has found the k collision for each input with type mu. Okay, so okay, does it answer your question how this works for the k-distinctness?
Yeah, I think so. I'm not too sure about the structure, but I see that you are trying to like partition your initial string into sort of solutions with some
Yes.
something like that. Yeah.
Yeah. So we'll come later why the steps are important. Okay. So that times they're just very handy to join different inputs within the same block. The same thing like in the same hidden subgroup problem. You have like your inputs like are like more dependent to a different subsets of your group. Sorry, subgroups of your group. Like than like with particular values of the which we have in this input. So in this case, it's also like this partition is more important than individual values of the elements. Okay, and so these elements in the knowledge systems are certificates. So if it contains a certificate, it is in the knowledge system. Okay, and so why I need this knowledge system? Define knowledge operator. Okay, so this on this slide is the statement of the knowledge system, the first point. Okay, so the knowledge operator is defined in the same way as this restricted transfer operator, epsilon mu, but I will denote it by this epsilon plus mu, where this L plus is is implicit. Okay, and what it does, it's somehow a filter. If the support of so it starts with the element of the Fourier basis of x, so it goes from x to y mu. So it starts with the uniform probability distribution, and that's why I've been talking about this uniform probability distribution for such a long time, because it's like the first half, the last half of this equation. So it starts with the Fourier basis, and then this knowledge operator just takes a look. It takes sigma, and tries to check whether the support of sigma lies in this knowledge system. The support is a subset of n, and knowledge system is a collection of subsets of n. So if the support of sigma is in this knowledge system, then it moves through. So it applies the transfer operator as before. So it's just epsilon mu sigma hat. And if it is not X, it blocks it. It says, sorry, it's 0. You are not going anywhere. Okay, so in other words, we use the Fourier decomposition in the uniform space X to define knowledge. That's because knowledge, as I said, I had this slide previously, that the sigma hat, so the support of sigma somehow shows which elements, which symbols of the input string the algorithm knows. Okay, in this branch of the superposition. Okay, and then I can define the Fourier decomposition only in the uniform space. That's why I need this uniform space. Okay, in the non-uniform space, it's much harder to define Fourier decomposition, Fourier basis. Okay, so and now I have this knowledge. I just use it and transfer it to my non-uniform probability distribution using the transfer operator. Okay, and altogether it gives me this knowledge operator. Okay, and again the total knowledge operator epsilon plus, so it goes from x to y. Okay, so y now is also imbued with these types, so it's both type and the input, and it's just a direct sum of individual epsilon plus mu. So again, just the same formula as before, but we had the same formula previously, but without pluses. Now it's with pluses. Okay, so now we have this knowledge system. So this is like the most important slide of the whole talk. So this idea, I think, is the most important, that we have this uniform probability distribution. We can define knowledge on them using the Fourier decomposition in the same way as Zhandry did, essentially. But now we can just move it to arbitrary probability distribution we care about using this transfer operator, and which is gives this knowledge operator, which is a filter whether I am using or I am not using the transfer operator, depending on whether the algorithm knows sufficiently much. If the algorithm knows something, then it goes through. Work now is similar to what I had previously. Let me go back to this anti-concentration slide, where I have this proposition of the final of the success probability of the algorithm, like assuming that the final state of the algorithm is strongly anti-concentrated. So where I introduced this anti-concentration previously. Now I'm going back to this framework. Yeah, now I'm having this decomposition of epsilon psi t, so which is the state of the algorithm, non-uniform, into two parts, which is epsilon plus and epsilon minus. Okay, well, epsilon minus is just a component of epsilon plus. It's just very easy to define. Okay, and now I have two things. If I can show two things. One thing is small knowledge. So this means that the algorithm has small knowledge about the input at the end. So this is formally, this is stated as the norm of upsilon plus psi t prime. So psi t prime is the final state of the algorithm, and I am applying the knowledge operator to it. And so, okay, psi t prime, of course, has norm 1. If I am applying upsilon plus, and so this means it has small knowledge. So it has at most delta knowledge. So this is one thing. And another thing is the same thing as before, but on the part which is, so I need anti-concentration on the part without knowledge on the upsilon minus, which is, so I need that it is, sorry, it should be strongly gamma anti-concentrated. Oh, no, sorry, it's okay. It's gamma anti-concentrated. I'm confused myself. So this is a subspace. This subspace should be gamma anti-concentrated. Okay, so this means that any state in this subspace is strongly gamma anti-concentrated. Okay, then the average success probability of the algorithm is at most gamma plus delta squared. Okay, so so this previous proposition on this anti-concentration slide is a special case of this if I am assuming that knowledge operator is just 0. If upsilon plus is 0, I am getting exactly the same thing as before. But now I'm having this decomposition, so it need not be that upsilon x at most t is gamma anti-concentrated, because usually it's not the case. But if I cut out the part which is maybe concentrated, so the part that has knowledge, which lives in upsilon plus, okay, it is allowed to be concentrated, okay, but I will show that the algorithm will not have great overlap with this subspace. Okay, so this is like the main thing of the whole construction. Okay, and so so another technical thing is just query gain. So how I will show that the algorithm has small knowledge. Yeah, so this is informal lemma. So this is what's written here actually is not true. Okay, but this like gives the flavor of what's happening. That upsilon, so this is the knowledge of the algorithm. I call this thing upsilon plus, the norm of upsilon plus psi t is the knowledge. So this is how much the algorithm knows about the input. Okay, and so so this thing on the left is the change in knowledge in one query. So this is the knowledge. This is the knowledge of the t queries. This is the knowledge of the t plus 1 query. So this is how much knowledge the algorithm has gained after one query. Okay, it's bounded by this psi partial thing. Okay, and this psi partial is defined in a quite easy but technical way. So for each I just take all the subsets that are on the verge of being in the knowledge system. So this is, maybe it's a bit hard to parse. Okay, but the idea, this is a subsets where I'm adding this element I. So this S is not in the knowledge system, but sorry, but it's on the verge. So this S, but it's on the verge of being in the knowledge system, because if I'm adding I, it is in the knowledge system. Okay, and so this gives me this correction of partial I. Okay, this is, and then I get this correction of operators, upsilon partial I, as before. So I don't write them out, but pretty much the same way. Okay, and this psi partial. So this is the reason why this psi here, but not upsilon, but okay, whatever. So that's just a direct sum over all i's, where I is the input thing. So this somehow measures the thing which is on the boundary. So how much is the algorithm learns during the query. Okay, and the point is that the norm of this vector here, if I employ partial, psi partial, is much smaller than the knowledge, than both of these things. So it makes sense to estimate the change in knowledge by the norm of this operator. And so why is this smaller? You can think about this as knowledge as being a ball. Yeah, and this partial psi is just the boundary of the ball. And the boundary of the ball has much smaller volume than the ball itself. Okay, and so that's why the state has much smaller norm. Yeah, so this is just things that's being added, and we can actually usually show that it's not so big. Okay, so using this lemma, which is informal, okay, I can combine with this framework, which is on the previous slide. okay, and show. So if I can prove this anti-concentration thing, and I can prove this small knowledge using this query gain, then I can show lower bound. So that's how the framework works. So any questions about this before I move on for the k-distinctness, which will be like much more high level overview. So any questions about the framework? So I know it's pretty technical, and okay, so let me now go to this problem of k-distinctness. Actually, the whole paper somehow, my talk on paper brings into 3 different levels. So one level is somehow this general framework. Another framework level is just framework for the search for equal elements, which I'm talking about right now. And the next one is just the thing that's specific for k-distinctness. Okay, now I'm just going about this search for equal elements. Okay, I already explained it before. So this is the set of types is given by the set of partitions. Okay, the partitions are linked to inputs if I and j share the same block. Sorry, the same value. So they share the same block if they share the same value of the input string. Okay, and so so it's also a special case of this is a hidden subgroup problem. I think I don't have this on the slides. Maybe I have later, I don't remember. But yeah, but this is the same thing we had for k-distinctness before. So I will relax this condition. That's why I need this q much larger than n squared. So I will assume that y mu, so this is the set of inputs with type mu, is just zq to the m, to the mu. So this means if you think about it, okay, I don't have this on slides again. So if you think about this here, okay, 2 inputs are in the same block. Okay, if they have, if and only if they have the same value. Now I'm assuming allowing like collisions between different blocks. So in each block, still all the inputs have the same value, which is given by this function on this block. Like all the elements of the same block have the same value, but I'm allowing collisions between different blocks. So I'm allowing that 2 blocks have the same value. For instance, I'm allowing the whole string have the same value. Okay, so this is some kind of accidental collisions. Okay, but if Q is large enough, there will be few of these collisions, and I can not worry about them. Okay, but what are advantages of this thing, of this relaxed condition, is that I can. So this is this y mu is just the set of functions from the blocks of mu into zq. Yeah, so this is what this z mu q means. So for each block, I have a value in zq, okay, which means that each element in this block has this value. Okay, and I can define Fourier basis, this tau hat, so mu tau hat. So mu is the type that is partition, and tau hat is the element of the Fourier basis in z mu. Yes, allowing. Yeah, so yeah, so so I thought about this relaxed condition. So where I have different. Okay, where I have different. I can assume. Okay, so sorry. I can allow the same value between different blocks. Okay, so this gives me this Fourier basis. Okay, and so the nice thing, this is like a very nice transfer operator between the Fourier basis. Fourier basis of x and Fourier basis of y is just the tau of b. So because of the tau is a Fourier basis on this mu, where the mu consists of blocks. So and blocks, each block is a subset of input indices. Okay, so on this term, that the tau of b is just the sum of all elements in the block of sigma I. So okay, the data was not so important, but there's like this very nice connection. Okay, so and that's why I'm using this relaxed version. Because now I can use also the Fourier basis both in x and both in y, and this is like very, very, very nice because I can like talk about different strings in sigma strings and tau strings, where sigma strings are strings supported on sigma on the n, and tau is the string supported on mu, supported on the blocks of the partition mu. Yeah, so let me give like a very simple example. So this is the element distinctness problem. So this is K2. And so I assume this is partition M mu I B. So where okay, A and B are in the same block and everything else is different. Okay, and so okay, and so this is the state of the so this is just state phi, which lives in X at most 2. So this is just something concrete to talk about. So so this is the normalization factor, which is square root of n choose 2. Okay, and so this is the sum over all functions. Okay, so this is just so this is n over 2 yeah, so this is yeah, so this one, so the functions over where v ranges over zq. So 1, okay, you can assume that the first element 1 gets mapped to v and 2 gets mapped to minus v. So this is the function. So this is sigma, this function defined on the elements of the n. Okay, so okay, and so it lives in X at most 2 because the support of this function is 2. Okay, if v is non-zero, it's 2. Okay, and it gets okay, and so this okay, so this is an element of X at most 2. So this is in the uniform space. Okay, and now I am applying this transfer operator epsilon phi. Okay, and so this epsilon phi looks like this. So if so let me go to the second term at first here. So this second term. Okay, so I have all possible. So assume that I have all possible partitions of this form. So I have 2 equal elements and everything else is singletons. But this AB can be located anywhere else, everywhere where I want. Okay, so this is given by mu IB. Okay, so if this mu IB is not 1 or 2, okay, then this 1 is going to the block that contains 1, and this 2 is going to the block that contains minus, to the block that contains 2. So one block is mapped to V, and another block is mapped to minus V. So this is the effect of the transfer operator epsilon. Yeah, because of this formula of the sums. So the value of the block is equal to the sum of the values of the elements inside the block. Yeah, but the interesting case is this mu 1 2 thing. Yeah, it goes to the empty. So in this case, if A is equal to 1 and B is equal to 2, then these both elements 1 and 2 end up in the same block. And so this means that this block gets the value which is the sum of the values, which is V plus minus V, which is the empty set, which is a zero function. Okay, so it gets, and I get q copies of this because there are q terms in this sum. Okay, and here I have like for each A and B, I have q vectors which are pairwise orthogonal. And so you see that this 1 2 somehow gets concentrated on this one block. Okay, and so if you work out the details, so this is the same thing. So you can decompose it as a there's the knowledge using the knowledge operator as epsilon plus and epsilon minus.
So
okay,
sorry,
the epsilon, yes.
In the previous, yeah, so this epsilon was not normal, not unitary, right? So it's eating some amplitude somewhere. So you start with a normalized state and then...
yeah, sure, yes. So I didn't tell about the probabilities. Yes, so the probability is, yeah, sorry, I forgot about that. Good question. The probability is that you take, so it suffices to assign probability to each mu AB, because for each mu AB, I will assume that I have a uniform probability distribution on all inputs with this particular type, right? So this is uniform, and mu AB are also uniform themselves. This means that each mu AB have the same probability distribution, which is essentially 1 divided by n over 2, and that's why I have the square root of n over 2 here. Yeah, thank you for asking. That's a very good question. Yeah, and yeah, so this is not uniform, but like in the confines of each type, it is uniform. But if you take just like in general, it's not. It's very far from being uniform. Yeah, and so this is like this division into the things that have knowledge and the things that doesn't have knowledge. The thing that has knowledge is concentrated on mu1, 2, and it has norm q. It has like norm q because this vector is like normalized. Yeah, and here it is underconcentrated. This part epsilon minus, which is the second term, it is underconcentrated, and it has norm like square root of n choose 2 times q, because n choose 2 is the number of pairs, and q is the number of terms in this sum over v. Okay, and so this is much larger than q if q is much larger than n squared, which I assume. Okay, so altogether epsilon x at most 2 is not underconcentrated because this vector is not underconcentrated, it's concentrated on mu1, 2. Yeah, but if I am just dividing into these two parts, so this turns out this part is underconcentrated and this part is concentrated but has no knowledge. Okay, and so, and if I measure this state, q is much larger than n squared, so I will get mu1, 2 with high probability. And so the small knowledge claim will show me that this will not happen. So it is not possible that the algorithm will have this state after 2 queries. But if you take, like, for instance, the probability, like without this knowledge thing, then you couldn't tell. It would be like a good state in x at most 2. It would seem as you would be able to get it after 2 queries, but in fact, you are not able to get it after 2 queries because it has very large knowledge, and it's possible to show that it's not possible. Okay, so I have this very generic underconcentration claim. Okay, not very generic, but somewhat generic. So if I have a set of partitions, assume it's symmetric under permutations, and another technical thing that has linear number of singletons. Singletons means box of size 1. Okay, this means that then epsilon minus of x at most t, so after t queries, I am underconcentrated for each t which is sublinear. Okay, so this is 1 over square root of n underconcentration claim. Okay, and so I have like 5 minutes or so. I will very briefly talk about k-distinctness. Okay, so it builds on the ideas of the search for equal elements. It's a special case thereof. So I also using this Fourier basis in x and Fourier basis in y. Okay, but now it has like a bunch of different things which I won't really go into because I don't have time, or I don't think you have enough energy to continue in the same place. Okay, so just very briefly. So this is like the worst case partition as follows. So this is a special case of k is equals 3. For arbitrary k, it's the same. So I have one k tuple. So one tuple of k elements which are equal, and then I have linear number of, in this case, 2 tuples and singletons. So I have the same number of tuples, so linear number of tuples of size less than k. Okay, and then I have this highlighted partition. Okay, so this means that one block of mu is highlighted, and so the knowledge system L plus mu consists of the supersets of the highlighted block. In this case, it's exactly the same thing as the same L plus I described before, because these 3 elements, this highlighted block, is a certificate. It's the only certificate here, which is the only kind of allowed 3 equal elements here. Okay, so if subset, if set is a superset of this triple, then it belongs to the knowledge system, which was used to define this knowledge operator. Okay, then this is not enough to prove the lower bound. So I will consider several collections of partitions at once, which are highlighted. Okay, and the difference is that I am taking this k tuple and I am chopping off a singleton. So this is M3 is the original one, M2 is 1 singleton chopped off, M1 is 2 singleton chopped off of this set of 3 elements, and one of these elements is highlighted. Okay, the algorithm doesn't know which one, but it has to find one, kind of. Okay, so only the first one on M3 is relevant to the lower bound, and this M2 and M1 are auxiliary. Okay, and so the main idea, if I'm taking two partitions, for instance, as in M3 and M2, so I'm just concentrated on this, this rectangle of 3 times 2 elements. So if I have two such partitions, then it turns out that this thing where I'm learning this new element I, yeah, so this is this epsilon delta I, which I was talking about, this query gain at the last slide of my framework. This is how much knowledge the algorithm gets after one query. It turns out that it's bounded by the knowledge of this mu1. Okay, so this is comparing to mu2, so it has to know all of this. And here it is the knowledge systems of mu1. It has to know all of this. So this means this is in the knowledge system, and so this I is not there, but really doesn't matter. Okay, and so this gives, just by really simple counting, this coefficient 1 over square root of n just comes from the normalization factors. This comes from the number of blocks. So this input has more blocks than this input. Okay, because like two of them are just joined together into one. Okay, and so this one over square root of n, just like very simple counting, very simple combinatorial element, just counting the number of elements into each of these mi's. Okay, and so this is bounds the query gain, like how much knowledge I gain by one query on the next level by the knowledge on the previous level, and it gets multiplied by n divided by square root of n. So somehow this is very formal, but it gives like a formal way to say that to find an L plus 1 tuple of equal elements, you have to find at first L tuple of equal elements, and then use Grover to find another element. So this is, you can think of this as 1 divided by square root of n is somehow complexity of the Grover search of additional element. So from the algorithmic point of view, this makes a lot of sense. And this is very simple to show from the lower bound element. This is just by counting. Okay, and then you need, so this is not enough to prove the lower bound yet. Okay, so I don't have the time to explain why, but just building on this idea and using some additional stuff, you can show the lower bound. But essentially, the main idea of the k-Distinctness lower bound is just this recurrence that bounds the knowledge gain of the next level by 1 over square root of n divided by the knowledge on the previous level. Okay, and yeah, so this part is not really complicated, but there is some additional stuff you have to work on. Okay, and so thank you. So actually, I was able to go through all the slides. Okay, so I'm open to your questions.